Hi again, everybody. So we've defined differentiability, we've given some examples. Now we want to write down a couple of consequences and characterizations. So the first one we hinted at the end of the last video, which is that differentiability implies continuity. So this is something people tend to get backward a lot. So differentiability implies continuity, meaning if your function is differentiable at a point, let me make this continuity, okay, then it is continuous at that point. The converse is not true. Now, having said that, another mistake that people try to make is I tell them, hey, try to prove that this function is differentiable at this point. And so they say, well, differentiability implies continuity, so I first have to show continuity. And that's not true. You can show directly that differentiability holds, right? Which in fact we did. You can see in the last example we did from the last video. We proved directly by using the limit of the difference quotient that the function h was differentiable at 0, and it is a consequence that h is continuous at 0. Okay, so you do not have to explicitly prove that. So the general statement here is going to be, right, so if we have a function f with domain D and A is some interior point of D, because again, we know we want D to contain an A coin, right? So when we defined it, we just said, okay, D contains an A coin, right? So alternatively, we could have said A is an interior point of D. Okay. Okay, so A is some interior point of D. If F is differentiable, and I'll abbreviate that as diff at A, then F is continuous. I'll abbreviate that as cont at A. Okay, so we're actually going to prove that here. Okay, so we know that D contains an A coin. Okay, so D contains an A coin, and because D contains an A coin, it follows that A is a limit point of D. Right? You have all these points in the A coin, and of course they converge to A. Fine. So one of our conditions for continuity when you have a limit point, so this implies that F is continuous at A if and only if the A limit of F is equal to F of A. Okay, so that's one of the cool properties of continuity. You try to compute the limit of the function at a point A, boom, you just put A right into the function. Okay, that only works with continuity. Okay, now, of course, I could rewrite this as the limit as x goes to A of f of x equals the limit as x goes to A of f of A. F of A is a constant, so putting a limit there doesn't change anything. Okay, fine. I can make this if and only if I know that the limit as x goes to A of f of x minus f of A is equal to 0. Now this probably looks obvious, but actually requires a little bit of explanation because, okay, if we knew that these individually were equal and existed and were equal, then of course I could subtract one to the other side, pull the limit out using the algebraic limit property, and then I would get exactly this equality in the bottom line. But what about moving upward? You see, you're probably thinking, well, sure, you can just split this at the minus sign, but that assumes from the beginning that each of the individual limits exist. Now, there's no question that the limit as x approaches A of f of A exists, but we have no assumption anywhere in our problem that the A limit of f exists. So this isn't simply as easy as, oh, use the algebraic limit property and break this back apart. Instead, well, we are using the algebraic limit property, but we do it in a more clever way. So let me do this on the side. So if I know that this limit of the difference of f of x and f of a is 0, then, so I have this limit, then of course it exists. So this exists, but I also know that the limit as x approaches a of f of a exists, and in fact it's equal to f of a. And so if I add those together, I'll get the limit as x approaches a of f of a. I know each of these limits individually exists. This one here is going to equal 0, and this one is just equal to f of a. But now, using the algebraic limit property, I can put these together. And I'll get the limit as x approaches a of, well, I get to toss all of this together. So I'll have f of x minus f of a, but then plus f of a. Well, the minus f of a and the plus f of a go away. I just get f of x. So in fact, this limit does exist, and it equals 0 plus f of a, which is f of a, right? Or I could put the limit here if I wanted. Doesn't change anything. So in fact, this bottom line does imply the one above it, which is important because that's the direction we need to be able to reverse up so that we can eventually end up at f being continuous at a. Okay, fine. So we've reduced our problem from showing that f is continuous at a to showing that the limit as x approaches a of the difference of f of x and f of a is 0. Now we get to our assumption. Our assumption was that f was differentiable at a. So f differentiable at a, well, that tells us that the limit as x approaches a of the difference quotient at a of f of x is equal to, well, whatever the derivative is, right? So this exists, okay? So we could call this f prime of a. Okay, what else then do we know? We know then that, well, the difference quotient, this is equal to f of x minus f of a divided by x minus a. Now, of course, we're trying to say something about f of x minus f of a, and well, that shows up in this difference quotient. So in fact, what can we do? Well, let's write down f of x minus f of a. That actually is equal to, well, if I take the difference quotient and multiply it by x minus a. So I take the difference quotient and multiply it by x minus a. Okay, but again, we know that this difference quotient, that has limit, whoops, this has limit f prime of a. And we also know that this x minus a, well, as x approaches a, this has limit 0. So this implies that the limit as x goes to a of f of x minus f of a is equal to the limit as x approaches a of dqa f of x times x minus a. And because each of these individual limits exist, the product of their individual limits exist. And we know that this is equal to f prime of a times 0, which is 0. And look, there we did it. We proved it, right? We showed the limit of this difference was 0. That's what we needed to show. That was equivalent to saying that f was continuous at a. Whew, that was tougher than expected. Okay, fine. So now we know that differentiability implies continuity. The other result I want to do in this video is to give an alternative characterization of differentiability, as we've done before, with sequences. Okay, so we have a new theorem. This will be our sequential characterization of differentiability. So this is great. Everything we do, we can take it back to sequences. All right, so as usual, we'll have some function with domain D. And I'm going to let A be some interior point so we can talk about the derivative at A. Okay, so f is differentiable at A. This is going to be if and only if. Oh, and with, I guess we should say here, right, with derivative f prime of A. Fine. If and only if, for every D not equal to A sequence. So I have a sequence A consisting of elements in D, but not including A itself. So this will be a D not equal to A sequence, which converges to little a. So I take any possible sequence of elements in D that don't contain elements of A, which converges to A. Okay, and so for each one, we have that if I apply the difference quotient based at A for F, and I apply it to this sequence A dot, of course, this gives me now a sequence, and it should converge to the derivative f prime of A. Okay, and this should be if and only if. Okay, now the proof of this is actually nothing new. This is simply the sequential characterization of functional limits, right? So if we go back to our sequential characterization of functional limits, okay, we have some function, we have a limit point. Okay, every interior point is a limit point. Then the limit of the function. So okay, so in our case, the function we're thinking about is going to actually not be f itself, but rather the difference quotient of f. Okay, so the difference quotient of f, and we take the limit of it, is equal to whatever this number, in our case f prime of A, if and only if, for every D not equal to A sequence A dot that converges to A, the difference quotient applied to A naught converges to f prime of A. Okay, so we can see it's just a specific case of the sequential characterization of functional limits. So that's fantastic. We don't have to do anything new, right? No new proof here. Okay, now a really nice consequence of this theorem, which is occasionally useful, is it gives us a way to enlarge our definition of differentiability slightly. So originally, when we defined differentiability at a point, we said, okay, you are only going to look at points A that are in the interior. Okay, so we assume that there is an A coin contained in D. However, the sequential characterization suggests a different way, right? So what if, for example, our D is equal to the closed interval AB? And I want to talk about differentiability at this point A. What should that mean? I can't put an A coin in D because A is on the boundary, right? So what would I do? But actually the sequential characterization suggests something. Look at all of the A dots, right? These D not equal to A sequences that converge to A, and look at whether all of their difference quotients applied to the A dot, right, converge to some number, okay? And if they do, then that should be the derivative at A. Okay, so you might think of this as allowing you to build one-sided derivatives by just looking at sequences of points converging to A. Okay. Now, of course, we only want this to be true when things are actually, limit points, right? In general, right? So, so let's just write down now here this definition. So, if A is in D and is not an interior point, right? So if it's an interior point, there's nothing to worry about. But if it's not an interior point, well, then if A is at least a limit point of D, then we say f from D to R is differentiable at A with derivative f prime of A if every, or if for every A dot, which is a D not equal to A sequence that converges to A. Okay, and I'm just copying now the sequential characterization. The difference quotient of f based at A applied to the sequence A naught converges to this number f prime of A. Okay, and this condition here that A is a limit point is important because if we don't assume that, then there may be no D not equal to A sequences converging to A, in which case this condition would be vacuously true. And so you would just say, oh, yeah, you're always differentiable at a point A, even if that doesn't really make any sense to talk about because A is maybe some isolated point. Okay. So that's going to be it for this video. In our next video, we're going to write down some of the common properties of the derivative. Video after that, I think we'll get into some of the big theorem consequences of differentiability, things like Fermat's theorem, Darboux theorem, etc. All right, we'll see you next time.